This will be the final video that regards periodic table, electron configuration, shortcuts, etc. Today is going to be an extremely useful thing to remember as we go through. We're going to deal with how it relates to valence counts. We're going to be talking a lot about valence electrons. Remember that valence electrons are the electrons in the highest energy level. So those are going to be really important as we go through some chemistry and why things happen. So let's just kind of take a look. Let's take a look at group 1. If we look at group 1, we'll see that hydrogen ends in 1s1, lithium 2s1, sodium 3s1, 4s1, 5s1, etc. So they all end in some kind of noble gas followed by S1. If we look at the previous noble gas, say for potassium, it would be argon. Well, argon, if we were to look before that, we would see that it ends in like 3p6, blah blah blah, then 4s1. So that 4s1 is actually the highest level. So if you were to do a valence electron configuration for potassium, it would just be 4s1. And if you did a valence electron configuration for francium, it would be 7s1. And so if you were to count the valence electrons for anybody in this group, it would have one valence electron. And by the same argument, the second column, the alkaline earth metals, everything that would all hold true again. 3s2, 4s2, 5s2, 6s2. So these would all have two valence electrons. And so you might be tempted to say, well, if we just count across the rows, across the columns rather, you'll find that there's 1, 2, 3, 4, 5, 3, 4, 5, 6, 7. You might start to think that, but that's actually not true, and let's see why. Well, let's look at scandium, for example. Scandium has an electron configuration using a noble gas shortcut of, you'll start with argon. And then you go to 4s2, and then if we look at scandium there, we see that's 3d1, and maybe I should go over that in red. I'm not sure how visible that is. Argon 4s2, 3d1. Now if you have the right kind of glasses on, that'll be 3d, right? So anyhow, let's count up valence electrons here. Well, the highest floor is not the third, but the fourth. So the number of valence electrons in scandium is still 2, because this is not a valence electron. It's the last one you put in, but it's not valence because the energy level is not the highest. So scandium has 2 valence electrons. And if we look at the next guy over, he's going to have another d electron, but no more s electrons. So those, in fact, everything in the d block has 2 valence electrons in its simplest form. We can complicate that a little bit, but we won't. But we'll just say that for now. But let's go over past the d block over to the p block now and see what happens over there. Well, if you get to, say, boron's configuration would be helium followed by 2s2 followed by 2p1. So if we count valence electrons here, we have 2 in the 2s and 1 in the p for a total of 3 valence electrons. And if you go to the next one down, you would see it also has 3. Aluminum would be 3s2, 3p1, and gallium would be 4s2, 4p1, and so on and so forth. Therefore, everything in this column has 3. By the same argument, if you want to keep playing it out, this column would have 4, this column would have 5, this column would have 6, this column would have 7, and this column would have 8. And so there you go. You now have sort of a list of valence counts in all of these columns. This column will always have 1 valence electron, an s1 electron. This column will always have 2. The transition metals will always have 2. Boron's group will always have 3. Carbon's group 4. Nitrogen's group 5. Oxygen 6. The halogen 7, and the noble gases 8. valence electrons. These groups 1, 2, 3, 4, 5, 6, 7, 8, that's one of our vocab words. Those are the main group elements, or representative elements. And what's special about them is you can just automatically look and see what their group number is. In fact, on your periodic table, you'll see this is Roman numeral 1a, Roman numeral 2a, Roman numeral 3a, 4a, 5a, 6a, 7a, 8a, and what those actually stand for is the valence count. Why are we making all this big deal about the valence count? Well, that's a lecture for another day, but it's a really huge important thing. The D block elements, they all technically have 2 valence electrons, as do the F block elements, but their valence count turns out is not quite as interesting or as important as the main group elements, as we shall see later. And so there you go, quick shortcut. You now know how many valence electrons are in any of the main group elements. You know that tin has 4, you know that chlorine has 7 valence electrons, potassium has 1, radon has 8, boron has 3. You can just immediately, boom, 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 find out how many valence electrons any of the main group elements has simply by what column it is in.